See this problem. A uniform magnetic field of 3000 Gauss is established along the positive z direction. A rectangular loop of sides 10 cm and 5 cm carries a current of 12 amperes. What is the torque on the loop in the different cases shown in figure? What is the force on each case? Which case corresponds to stable equilibrium? Our motive is to find the torques acting on these loops, which are given in these 6 pictures. Here the magnetic field direction is same in all pictures, but the areal vector of each loop is changing. So by considering these two, we need to find out the torques and forces along with the case which is having stable equilibrium. So our motive is we need to find out different torques and forces along with the cases which have stable equilibrium. That is our motive. Now come to investigation part. The magnetic field B is equal to 3000 Gauss. So in SI system it is 3000 into 10 to the power of minus 4 Tesla, or I can write 0.3 Tesla, and A is equal to length into breadth. So everywhere it is length and breadth are same. So 10 into 5, that is equal to 50 centimeter square, or 50 into 10 to the power of minus 4 meter square, and current flowing in the loop I is equal to 12 amperes. So these are the given quantities. Now come to the resolving part. We will resolve one by one. I am considering the first problem. So in this picture the magnetic field is towards positive z axis. So I can write the magnetic field in terms of unit vector k. And come to area vector. Here the current is flowing in anti-clockwise direction. If you turn your right hand fingers into this way, the thumb which is showing is the areal vector direction. So that is in positive x direction. I can write the given quantities with directions as B is equal to 0.3 k cap. It is the unit vector in positive z axis direction, Tesla, and A is equal to 50 into 10 to the power of minus 4 I cap meter square. I is the unit vector towards the positive x-axis, and current I is equal to 12 amperes. Now tau is equal to I into A cross B, that is equal to 12 into 50 into 10 to the power of minus 4 I cap into 0.3 into k cap, that is equal to, I am taking numerical part to one side, 12 into 50 into 10 to the power of minus 4 into 0.3 into I cross k. The resultant of I cross k is minus j. If I multiply this thing, I will get 1.8 into 10 to the power of minus 2 Newton meter in the direction minus j. Minus j in the sense it is in negative y-axis direction. That is, this is the negative y-axis direction. So the direction of the torque is towards negative y-axis. Now come to the second picture. In this also the magnetic field is acting towards z-axis. So this is the direction, and here though the coil is put it into horizontal way, the direction does not change. So it is moving in anti-clockwise direction. So the normal vector, that is areal vector, is towards x-axis only. So here the magnetic vector direction and areal vector direction is not changing. So the resultant also does not change. So torque acts towards negative y-axis, and the value of torque is B is equal to 0.3 k cap Tesla, A is equal to 50 into 10 to the power of minus 4 meter square in the direction I cap, and tau is equal to I into A cross B, which is equal to 1.8 into 10 to the power of minus 2 Newton meter in the direction minus j cap, that is minus y-axis. Now come to the third picture. So here the current is flowing in this direction. So from this I can guess the normal vector direction towards the negative y-axis. And if it is in negative y-axis and magnetic field is in positive z-axis, then the resultant vector, that is torque's direction, is towards the negative x-axis. B is equal to 0.3 k cap, A is equal to 50 into 10 to the power of minus 4 meter square minus j cap. I is equal to 12 amperes. So tau is equal to I into A cross B, that is equal to 12 into 50 into 10 to the power of minus 4 into 0.3 into minus j cross k. J cross k gives I cap. After multiplying this, I will get 1.8 into 10 to the power of minus 2 and minus I cap. So that means it is in negative x-axis direction. Torque acts towards the negative x-axis direction. Now come to the fourth picture. In the picture, the loop turned to some 30 degrees from y-axis. So then it is making 60 degrees with the x-axis. So on the top view, I can write like this is y, this is x-axis, and this is your loop whose normal vector is towards x-axis like this earlier. Now you are turning to 30 degrees. So here it is 30 degrees. Then this angle becomes 30 degrees. How it became 30 degrees? If it is 30 degrees, here the angle becomes 60. So this is a right angle triangle. So here it is 30 degrees. So that corresponding angle is 30 degrees itself. So aerial vector is making 30 degrees with the positive x-axis. Then I can write the aerial vector as A is equal to AX I cap plus AY j cap, that is equal to, here AX can be written as 50 into 10 to the power of minus 4 cos 30 degrees I cap plus 50 into 10 to the power of minus 4 sin 30 degrees j cap. But here the other component of the A is in negative y-axis direction. So I can write minus here, that is equal to 50 into 10 to the power of minus 4. I am taking it as common, is equal to cos 30 is root 3 by 2 I cap minus sin 30 is 1 by 2 j cap. So this is the aerial vector, and B is equal to 0.3 Tesla k cap. Now resultant tau is equal to I into A cross B. I is current, so 12 into A is 50 into 10 to the power of minus 4 and root 3 by 2 I cap minus 1 by 2 j cap cross B is 0.3 k cap, that is equal to, I am taking integral part at one side, 12 into 50 into 10 to the power of minus 4 into 0.3 into root 3 by 2 I cap cross k cap minus half into j cross k cap, that is equal to 1.8 into 10 to the power of minus 2 into root 3 by 2 I cross k is minus j cross k is I, so half into I cap. By observing this, I can say the torque vector is towards a negative x and a negative y axis. That means it will lie in this quadrant. This is negative x axis direction, this is negative y axis direction. The torque exists in this direction. So the magnitude of the torque here is root of tau x square plus tau y square. So you will get here 1.8 into 10 to the power of minus 2 Tesla itself. And come to the direction, tan theta is equal to tau y by tau x. So tau y is here root 3 by 2 into, we need to consider this also, but this component is also having this value, so those two will get cancelled. The remaining thing is root 3 by 2 by 1 by 2, that is equal to root 3. So tan theta is equal to root 3, then theta is equal to 60 degrees. So theta is equal to 60 degrees in the sense this vector, tau vector, is making 60 degrees with the negative x-axis. So I can calculate the angle from positive x-axis as this is 180 and 60, so total 240 degrees. So the resultant vector, that is tau, is making 240 degrees with the positive x-axis, and the resultant magnitude is 1.8 into 10 to the power of minus 2 Tesla. Now come to the fifth question as well as sixth question also. Here the current is flowing like this. So the aerial vector is towards positive z axis, and here it is in this direction. So aerial vector is towards negative z axis. Here the aerial vector is in the direction of the magnetic field direction. So the cross product becomes 0. Then tau is equal to I into A cross B, that is equal to I into A into B. A direction is towards z axis, so I can write K cross. B direction is also towards z axis, so I can write K cross. K cross K is 0, so tau is equal to 0, force is equal to 0. And come to this case, here also tau is equal to I into A cross B, that is equal to IAB. A is towards negative z axis, so minus K I can write cross K. So this will become 0. Tau is equal to 0, F is equal to 0. So come to this picture. Here the aerial vector is towards the magnetic field direction. Then it will attain stable equilibrium, because if you give a small amount of force to turn this, it will regain its position. It will be towards the direction of the magnetic field. Here if you give a small amount of force to turn this coil, it will regain its position. So it is called stable equilibrium. But in this case, if you apply a small force to this coil, it won't retain its position, like not in negative z axis direction, but it goes to positive z axis direction, because it is not in stable equilibrium. It is in unstable equilibrium. So a small force will turn this coil towards the magnetic field direction, and the forces in all these 6 cases is 0, because first 4 cases the coil is turning due to couple acting on it. So couple creates 2 equal forces in opposite direction, so net force acting on the coil is 0. And in last 2 cases, whether it is stable equilibrium or unstable equilibrium, so the force acting on those 2 coils is 0.